Welcome to the new episode of our podcast, AI Talk. Today, your host will delve into vectors, a key element that has become an integral part of software development in recent years. It's astonishing but true. Progress in the field of programming and artificial intelligence in particular is radically transforming the world of new technologies. It is the architecture of transformers, relying on the power of parallel computations, that has become the catalyst for this progress. The same principles underlie modern processors, including graphics cards, which use parallel computing to achieve high performance. All of this has been made possible thanks to vector mathematics, which lies at the foundation of transformers. Imagine how this mathematics sets an entire industry in motion today. Vectors are mathematical objects possessed with spatial orientation. Their main task is to identify key directions and determine the intensity of movement towards a goal. By mastering vectors, you will gain a universal tool for navigation not only in the three-dimensional world, but also gain an additional advantage for working in the multidimensional spaces of artificial intelligence. This knowledge opens doors to the world of complex data and algorithms, expanding the boundaries of what's possible. Surprisingly, from a mathematical notation perspective, a vector is simply a series of numbers separated by commas. But these numbers carry a profound meaning. They define the direction and magnitude of movement in space. Thus, vectors, being an abstract set of numbers, perform a key function. They determine the direction and magnitude of movement towards a goal. They allow us to assess how close we are to the goal and whether we are moving in the right direction. It's akin to driving a car. We follow the navigator's instructions, adjusting speed and direction with the pedals and steering wheel. Vectors also enable AI to not only determine direction and force, but also to assess proximity to a goal, compare objects, and highlight significant elements in data. Vectors in three-dimensional space are closely linked to geometry, and we represent them as three numbers corresponding to the coordinates of a point. By connecting this point to the origin, we get the classic representation of a vector. However, by adding a fourth number, we move into an abstraction that is beyond human visualization. In multidimensional spaces, such as AI, each new number adds a dimension, creating vectors that we cannot visually represent but can mathematically utilize. This understanding is crucial for working with vectors in machine learning and AI. Even in multidimensional spaces, we retain the classical understanding of a vector as a directed segment. The idea of representing a vector as an arrow indicating the direction of its action remains relevant in these spaces. We accept that vectors indicate directions, even if they extend beyond our three-dimensional perception. This concept helps us work with vectors in any dimension, including those used in artificial intelligence and machine learning. While vector mathematics, applied in the multidimensional spaces of artificial intelligence and transformer architectures, is not subject to visual representation, each mathematical operation has a clear and intuitively understandable meaning. Remarkably, operations used in vector geometry work similarly in the context of artificial intelligence. Let's consider the main operations on vectors, how they are performed, what geometric meaning they carry, and their practical application in the development of neural networks and machine learning. In the world of mathematics, where every action and symbol has its meaning, vector operations hold a special place. They did not arise out of nothing, but as a response to practical challenges faced by scientists and engineers. Here are the main operations on vectors. Vector addition, combining two vectors to obtain a new vector, the direction and length of which depend on the originals. An example is determining the total displacement when an object moves first in one direction and then in another. Vector subtraction, finding a vector that indicates the difference between 2 points in space. It's like finding the shortest path from one point to another. Multiplication of a vector by a scalar, changing the length of a vector without changing its direction. This is used, for example, when scaling objects in graphic design. Dot product, determining the angle between two vectors and calculating the projection of one vector onto another. This is used to determine the orientation of objects relative to each other. Cross product, creating a vector perpendicular to the plane formed by two original vectors. This is a key action in computer graphics for defining surface normals. Each of these operations has its origins in real-world tasks, from navigation and cartography to architecture and aerodynamics. Mathematicians may be fascinated by abstraction, but their work is inextricably linked to the real world and its needs. For example, the dot product helps pilots understand how much their course intersects with the course of another plane, and the cross product is used to calculate the moment of force in physics. These operations are not just mathematical games, they are tools for solving the problems we face every day. Vector addition is akin to constructing a route where each vector represents a separate stage of the journey. In geometry, we take one vector and place its beginning at the end of another. If we imagine vectors as arrows, their tips indicate the direction of movement. By adding two vectors, we obtain a new vector that shows the total displacement from the starting point of the first vector to the end point of the second. This is the result of addition, a new vector that reflects the cumulative movement in a specific direction. In neural networks, particularly in transformer architectures, vector addition is performed using tensor operations. A tensor is a multidimensional array of numbers that, in the context of AI, can represent, for example, word vectors, embeddings. When a transformer processes text, it sums the word vectors, considering their context, which allows refining the meaning of each word in a sentence. This summation of vectors helps the model determine which words are important in a given context and guides the learning process towards a more accurate understanding of language. Similarly, if a transformer works with images, it can sum vectors representing different parts of an image to identify key features or objects. This allows the model to understand the image as a whole based on the data that has been loaded into the system. Thus, vector addition in machine learning is not just a mathematical operation, it is a way of translating data into a multidimensional space where each direction has its significance. And each step brings us closer to understanding the essence of the data, whether they are words, phrases, or images. This is the foundation for creating models capable of recognizing, interpreting, and responding to complex queries. Vector subtraction in geometry can be visualized as finding the shortest path between 2 points. In programming, especially in transformers, vector subtraction can be used to determine the difference between elements, for example, between two words or phrases, to improve understanding of context. In machine learning, vector subtraction can help a model understand the difference between different classes or categories of data. For instance, if we are working with vectors representing images, subtracting one vector from another can show what features distinguish one image from another, which is important for classification tasks and pattern recognition. This makes vector subtraction a valuable tool for identifying unique characteristics in a dataset. This is particularly useful in computer vision tasks, where it is necessary to classify or differentiate objects from one another. Multiplying a vector by a scalar is an operation that allows changing the size of the vector while maintaining its direction. It's like changing the scale of a map. We increase or decrease distances, but keep the proportions and directions intact. In the context of AI, this can be used to adjust the weights of features in the data, making some aspects more or less significant in the model training process. The dot product is a measure of how aligned two vectors are. It can be compared to determining how much two directions coincide or oppose each other. In AI, the dot product is used to calculate the similarity between vectors, which can aid in classification or clustering tasks. Let's reflect on the benefits of vector subtraction and the dot product in the context of the attention mechanism of transformers. Vector subtraction in the attention mechanism of transformers plays a key role in identifying differences between elements. When we subtract one vector from another, we are essentially measuring the distance between them in multidimensional space. This allows the transformer to reveal the unique characteristics of each element, distinguishing it from others. Thus, vector subtraction helps the model determine which data elements are unique or anomalous, which is important for highlighting key points in the information stream. The dot product, on the other hand, allows us to assess the degree of similarity between vectors. This operation turns multidimensional vectors into a single number that reflects their mutual position in space. In the context of the attention mechanism, this number is used to evaluate how similar one element is to another. Thus, if the dot product is large, the elements are considered similar, which allows the model to establish connections between similar elements and highlight them as significant for further analysis. Both operations, subtraction and the dot product, have a common goal. They help the transformer understand the structure of the data by highlighting important elements and relationships between them. However, they do it differently. Vector subtraction focuses attention on differences, while the dot product emphasizes similarities. In the attention mechanism of transformers, these operations are used to create an attention matrix that determines which elements should be focused on when generating a response. Vector subtraction helps the model filter out irrelevant information, while the dot product helps identify key points that will be used by the decoder to form new content. Thus, vector subtraction and the dot product are two sides of the same coin. They are both necessary for the full functioning of the attention mechanism, allowing the transformer to effectively read and understand the data it works with. The cross product creates a new vector that is perpendicular to both original vectors, thus forming the basis for determining three-dimensional orientation. In computer graphics, this is used to create normals, which determine how light reflects off surfaces, giving objects a realistic appearance. Although the cross product is not as widely used in transformer architectures as addition or the dot product, it still has its place in certain specialized applications. For example, the cross product can be used to create orthogonal vectors, which can be useful in tasks where it is necessary to maintain the independence of features or dimensions. In the context of the attention mechanism, the cross product can be used to determine the degree of uniqueness in the interaction between pairs of elements. If two vectors form a large vector as a result of the cross product, this may indicate that their interaction leads to the creation of new, independent information, which can be useful for the decoder when generating responses. While the cross product is not a primary operation in standard transformers, it can be used in more experimental or specialized models where orthogonality or uniqueness of interactions between data elements needs to be considered. Vector operations not only provide a mathematical toolkit for working with data, but also allow us to visualize and interpret multidimensional spaces, which are key in machine learning and AI. They enable models to understand complex data structures and extract valuable information from them, forming the basis for decision-making and predictions. Thus, vector mathematics is a fundamental tool in AI development, allowing models to learn, adapt, and perform complex tasks that would be impossible without understanding and applying these concepts. In our next episode, we will discuss how vector operations are applied in specific machine learning algorithms and what innovative approaches are used in modern AI systems. As we draw the curtains on today's enlightening journey through the intricate world of vector mathematics and the transformative power of AI, we have a special auditory treat for you. In a harmonious collaboration between two neural networks, one has artfully crafted a textual description in English, capturing the spirit of today's discourse in a single, evocative sentence. This description, imbued with the essence of innovation and the rhythm of discovery, served as the muse for the second neural network, which in turn composed a melody that resonates with our theme. We proudly present to you Quantum Rhythms, a musical embodiment of today's exploration, a symphony where each note echoes the leaps and bounds of AI and vector mathematics.
Floating through the vast unknown in a world of numbers I have never known, discovering the patterns, the codes untamed, unleashing our minds, a symphony unchained, exploring the depths of AI's mind, where dreams and reality intertwine, with every line of code and theorem we find, creating a symphony within the binary grind, unveiling the secrets of the universe's core. In the realm of vectors, we forever soar, embracing the beauty that math ignites in this world of innovation. We find our light. We find our light.
Thank you for lending us your ears and minds. Until next time, keep tuning in to AI Talk for more insights where technology meets imagination.
AI Talk, where the future is now. Today, let the rhythm of progress lead you somehow. Imagine the soundscape that pulses with innovation, a melody that defies all limitation. We're breaking barriers, we're pushing the line.